sklearncovariancegraphicallasso. Description: explain in detail. Graphical lasso is a method for estimating sparse covariance matrices. It is particularly useful when the number of variables is large, and the true covariance matrix is likely to have many zero entries. The method uses a penalized likelihood approach, where the penalty term encourages sparsity in the estimated covariance matrix. Inputs. Input 1. Explain in detail. EMPCOV. The sample covariance matrix to be regularized should be a 2D array with shape n features. N features. Input 2. Explain in detail. Alpha. The penalization parameter controlling the sparsity of the estimated covariance matrix. Higher values result in sparser matrices. This value must be strictly positive. Outputs. Output 1. Explain in detail. Precision. The estimated precision matrix inverse covariance. It is a 2D array with shape n features. N features. Output 2. Explain in detail. Covariance. The estimated covariance matrix. It is a 2D array with shape n features. N features. Steps. Step 1. Explain in detail. The graphical lasso algorithm works by minimizing a penalized likelihood function. The penalty term is a multiple of the L1 norm of the precision matrix, which encourages sparsity in the estimated precision matrix. Step 2. Explain in detail. The algorithm iteratively updates the precision matrix until convergence. Metrics. Metric 1. Explain in detail. The most commonly used metric to assess the performance of graphical lasso is the log likelihood of the estimated covariance matrix on the data. Metric 2. Explain in detail. The sparsity of the estimated precision matrix can be measured by a number of non-zero entries. Visualization plots. Visualization plot 1. Explain in detail. The estimated precision matrix can be visualized as a graph, where each node represents a variable and an edge between two nodes indicates a non-zero entry in the precision matrix. Visualization plot 2. Explain in detail. The sparsity pattern of the estimated precision matrix can be visualized using a heat map, where the color intensity represents the magnitude of the entries. Fine-tune parameters. Parameter 1. Explain in detail. Alpha. The penalization parameter. This parameter controls the sparsity of the estimated covariance matrix. Higher values result in sparser matrices. You can experiment with different values of alpha to find the best balance between sparsity and accuracy. Parameter 2. Explain in detail. Maxiter. The maximum number of iterations to perform. You can adjust this parameter if the algorithm is not converging within a reasonable number of iterations. Uncertainty methods. Uncertainty method 1. Explain in detail. Bootstrap. One way to assess the uncertainty in a estimated covariance matrix is to use bootstrap resampling. This involves repeatedly sampling with replacement from the original data and estimating a covariance matrix for each bootstrap sample. Uncertainty method 2. Explain in detail. Cross-validation. Another approach is to use cross-validation. This involves dividing the data into training and validation sets and using the training set to estimate the covariance matrix and the validation set to assess the performance of the estimated covariance matrix. Challenges and fixes. Challenge 1. Explain in detail. High dimensionality. When the number of variables is very large, the graphical lasso algorithm can be computationally expensive and may not converge to a good solution. Estimating the covariance matrix for a dataset with 1000 variables. 1. Use a more efficient algorithm, such as the block coordinate descent algorithm. 2. Reduce the number of variables by performing feature selection. Challenge 2. Explain in detail non-convergence. In some cases, the graphical lasso algorithm may not converge to a solution. Estimating the covariance matrix for a dataset with highly correlated variables. 1. Increase the Maxiter parameter. 2. Try a different value of alpha. 3. Use a different algorithm for estimating the covariance matrix.